So we're just going to cover one section from this chapter, balancing redox reactions. A little bit of review here, which isn't that necessary because we just talked about this. Oil rig oxidation is loss of electrons, reduction is gain of electrons. Oxidation is an increase in the oxidation state, reduction is a decrease in the oxidation state. So when we look at the reaction between calcium and water, calcium hydroxide and hydrogen gas form, we can identify the oxidation states of everything involved and see that calcium is going from 0 to +2, it's being oxidized. The hydrogen is going from +1 to 0, it's being reduced. There has to be an oxidation with a reduction, they have to go together. So mass has to balance, and here we see there's a calcium, and there's 4 hydrogens and 4 hydrogens, 2 and 2, and 2 oxygens and 2 oxygens. But charge also must balance. And if you take a redox reaction and just balance it with respect to mass, it doesn't always work out that the charges balance as well. So we're going to learn the half reaction method for balancing redox reactions. We take the equation and we break it into 2 half equations, half reactions. We balance them individually and we put them back together. So we need to be able to identify the oxidation states of the atoms and identify what's oxidized and reduced. This step doesn't necessarily need to be written down. Step 2, separate the overall reaction into 2 half reactions. One will be for oxidation and one will be for reduction. But you don't actually have to label them if it doesn't require you to do so. And then we're going to balance each of the half reactions. First, we balance with respect to mass. Balance everything other than H and O. Then we're going to balance oxygens by adding water and balance hydrogens by adding hydrogen ions. This is balancing aqueous redox reactions in acidic solution. So because it's aqueous, there is water present. So if we need oxygens, we can just put water in as a reactant or a product wherever we need to. And it's not making anything up because all of this is occurring in a solution of water. And then we balance the hydrogens by adding hydrogen ions. It's an acidic solution. There is an excess of hydrogen ions present as well. Then we're going to balance each half reaction with respect to charge. Make sure that the charge on each side of the arrow is the same. We're going to do that by adding electrons. So you'll have one reaction where electrons show up in the product and one reaction where they show up as a reactant. Then you look at your 2 half reactions and you need the number of electrons in each of them to be the same so that when you add them together they cancel out. So this may involve some multiplying. You add the half reactions together, cancel electrons and anything else that occurs on both sides, and then you check the balance with respect to mass and charge. So those are the steps. We're going to do some examples. In the first couple of examples, I've got kind of a short list of the steps over here just to remind us. Assign oxidation states. Here this H plus is a +1 and H2, this is an element that's going to be 0. Chromium here, no charge, that's 0, and over here it's got a charge, it's +2. Separate into 2 half reactions. So here I've got 2 reactants. One will be the reactant for each of the half reactions. So I'm going to start, and it really helps if you keep your arrows lined up. So I'm going to put hydrogen ion as the reactant for my first half reaction and chromium for the second half reaction. And then I want to take the products that are listed and match them up. So hydrogen ion, is that going to make H2 or is it going to make chromium? It's got to be H2, right? You can't turn hydrogen into chromium, not in a chemical reaction. So H2. Leave yourself a little space in case you need to stick a coefficient in there. And then the chromium must be going to the chromium ion. And there's my two half reactions. Your book labels them oxidation and reduction. You can balance it just fine without thinking about that. Okay, so we did this and we did this. Balance with respect to mass. So here I've got H plus and here I have H2. Is that balanced with respect to mass? No. So if I put a coefficient in front of the H plus, now it's balanced. How about the second reaction? One chromium on each side, that's balanced. Okay, so there I went with mass. Now I have to balance with respect to charge. For this top reaction, the total charge on the left side of the arrow is +2, and the total charge on the right side is 0. Are those the same? No. I'm going to add electrons to one side or the other to get them to be equal. So I've got +2 charge here. If I add 2 electrons on this side, then the 2 negative charges and the 2 positive charges add up to 0, and the other side is 0. Okay? In the bottom, I've got a 0 charge on the left and a +2 on the right. Again, they don't necessarily both have to end up 0. A lot of times that happens, but not always. They just need to be the same. And the only thing you can add is electrons. So here I need to add electrons to the product side. 2 negative charges here with the 2 positive charges. Total of 0 on this side, 0 on the other side. Any questions?
So with these ones, it does go both ways.
Well, so what we're going to see is that we've got one that is gaining electrons and one that's losing electrons. One is an oxidation, one's a reduction. Okay, so that was step 4. Make the numbers of electrons equal. So in this top reaction, I had 2 electrons on the left. The bottom reaction, I have 2 electrons on the right. It's 2 electrons for both of them. So that one took care of itself. Now I'm going to add them together. So I've got 2 electrons on the left and 2 electrons on the right. So those are kind of like spectators, right? They go away. What's happening is that this half reaction is producing electrons and this one is taking them. And so we don't see the electrons in the overall reaction. So the electrons should always cross out because when we made the electrons numbers equal, we did it so they would cross out. And then I'm just going to copy down what's left. And I've got 2H plus aqueous plus Cr solid to make H2 gas plus Cr2 plus. Verify. Got 2 hydrogens, 1 chromium, 1 chromium. Total of +2 and +2 balanced. This is an equation that you could balance just by inspection and come up with the right answer, but a lot of them you can't. Any questions about this one? Let's do this one now. The steps are missing. So we have iron going from +2 to +3. That's a change, right? And here we have manganese 2+, and we could figure out what the charge or the oxidation state is for the manganese here. We can actually balance the thing without doing that. Let's skip it. And we write 2 half reactions. So I've got 2 different reactants this time again. We've got Fe 2+ aqueous, and I've got, that's permanganate ion. And the Fe2 plus is most like the Fe3 plus, so that's going to go over here. And the Mn2 is the most like this one. This is one that would be hard to balance by inspection because there's oxygen on this side and there's no oxygen on that side. Can't just throw coefficients in there. Okay, so I split it into two half reactions. Now I balance with respect to mass. So the top half reaction, is this balanced with mass? Yeah, there's one iron ion and another iron ion. Their charges are different, but that's another problem. Here I have one manganese and one manganese, and I have 4 oxygens here and none. I need to add water because that's what the steps tell me to do. So I'm going to add H2O, which is a liquid. We're assuming room temperature. How many of those do I need to get 4 oxygens? I need 4 water molecules to get 4 oxygens, right? Is it balanced now? No, now I've added H in them, so that's all messed up. It's an acidic solution. We balance the H with H+. So I've got a total of 8 hydrogens over here. So I'm going to fix this by adding hydrogen ions over here. And I need 8 of them. Now are all the elements balanced? Yeah. 8 hydrogens on each side, 1 manganese on each side, 4 oxygens on each side. Next, we balance with respect to charge. So this top one, I've got +2 on one side, +3 on the other side. From the acidic solution. Yes, I added water over here, and that fixed the oxygens, but it introduced hydrogen, and then I have to balance the hydrogen, and so I do that by adding H+. Which seems a little bit like I'm pulling things out of the air, but I'm actually pulling them out of the solution. So these things are all aqueous. They're in water, right? So most of the water just doesn't do anything, but some of the water might be involved in the reaction. And it's acidic, and so that tells me that there's hydrogen ions in the solution also, and so I can just put hydrogen ions in there to balance the hydrogens in the water. Seems a little weird, but I'm not just making things up. So +2 and +3, I need them to be the same by adding electrons. So if I add 1 electron over here, this -1 and a +3 gives me a total of -2 on that. I'm sorry, +2 on this side and +2 on that side. And then the other one, down here I've got +2 charge on this side and 8 and -1 +7 over there. Right? So I have a +8 and a -1, and that adds up to, let's put it over here, +7. And over here, I've just got the +2. I need them to be the same. They're not going to be 0. I just need them to be the same. So how do I make a 7 into a 2? I need 5 negative charges, right? 5 electrons. So now I have a -5 and a +8 and a -1, and those add up to +2. Same as this side. Are you okay with that? The math here is very simple. It's just adding, but it's adding positive and negative numbers, and it is a bit abstract. So it can be a little tricky sometimes. So I want to be able to add these two equations together and have the electrons cancel each other out. But here I've got 5 electrons that I'm using, and this is only giving me 1 electron. So what I'm going to do is I'm going to multiply all the coefficients by the same number until I get what I want. So if I put 5 iron 2s, making 5 iron 3s plus 5 electrons, is it still balanced? Yeah, I did the same thing to everything. It's still balanced, it's just 5 times as much. But now I've got 5 electrons here and 5 electrons there, and when I add these together, I can cancel out the electrons. So 5 electrons and 5 electrons. And then I'm going to copy down what's left. So 5 Fe 2 plus aqueous plus 8 H plus aqueous plus MnO4 minus aqueous gives me 5 Fe3 plus aqueous plus Mn2 plus 4 H2O. And you should go through and check and make sure that the charges add up to the same number on each side and that you have the same number of each element on each side. Any questions? Mm-hmm.
Are the there's only 3, then 2 plus 2, and there's plus 5?
So over here I have
Or
plus
do you multiply the 5 and the
plus
2?
10
Oh, okay.
and plus 8 and minus 1. And then here I have plus 15 and plus 2. Any other questions? Let's do one more example in acidic solution. So I'm going to split this into 2 half reactions. So I've got copper and I've got nitrate. And copper matches up with Cu2 plus, the copper ion. And then this NO2 is most like the NO3. Details are important here. This has a -1 charge. This one does not have a -1 charge. It kind of looks like nitrite ion, but it's not nitrite ion, it's nitrogen dioxide. Very different. So first I balance with respect to mass. 1 copper, 1 copper, good. 1 nitrogen, 1 nitrogen, but 3 oxygens and 2 oxygens. I need another oxygen on the right side, and I do that by adding water, because that's what the directions say. Because that's where the oxygen is going to be. So that fixed my oxygens, but it introduced a problem with hydrogens, and so here I've got 2 hydrogens, and I need 2 hydrogens on the other side, and so it's an acidic solution, so I'm going to add 2 H plus ions. And now I've got the correct number of elements on each side. Now I need the charges to balance. So on the left I have 0 charge, on the right I have +2. The only way I can balance this is by adding electrons, which are negative. So if I add 2 electrons here, -2 and +2 add up to 0, and 0's over there. You should always end up with one reaction having electrons in the product side and one on the reactant side, because you should have one oxidation reaction, one reduction. Down here on the right side, 0 charge. On the left side, what's the total charge? So I have +2 and -1. Those add up to +1, right? So to get a 0 charge, I need 1 electron. This is the sort of thing that can just twist around in your head. And so, if you find yourself getting it wrong, write it down. Okay, what do I do now? I need to multiply my bottom equation by a number to make the number of electrons here equal to the number of electrons up there. So this time I'm going to multiply everything by 2. I need 2 electrons. So if I multiply 2 times 2, I get 4 there. This is a 2, and a 2, and a 2. I need there to be 2 electrons in this equation because there's 2 electrons up here. And when I add them together, I need the electrons to cancel out. So now that I've accomplished that, when I add these together, 2 electrons and 2 electrons are going to cancel out. And I'm going to copy down what's left. The exact order that you write these in doesn't matter. And if you check that, you'll find that it is balanced. Questions?
What's the point of doing this?
That's a good question. What's the point of doing this? Okay, so how can I balance this equation without doing that? Because here I've got 1 copper and 1 copper, 1 nitrogen, 1 nitrogen, 2 oxygens, 3 oxygens. If I just put coefficients in front of these, I'm going to go around in circles forever. I could throw an H2O over here, and I could throw some hydrogen ions over here. But the problem is that when the copper is oxidized, it loses 2 electrons. 2 electrons have to be gained by whatever's being reduced. And just doing it by inspection sometimes is possible, but sometimes you get something that looks balanced, but it actually isn't balanced with respect to charges, and it's actually much harder than doing it this way. It's an excellent question. This is not one of those essential skills like stoichiometry, unit analysis, calculating molar masses, that sort of thing. This is one of those things that's on the list of things we're supposed to cover. And if you want an A in the class, you should do your best to get this stuff down. Okay, what if we have a reaction occurring in a basic solution instead of an acidic solution? There's one thing extra we need to do. And I've done this a couple of different ways. Basically, you're going to do the same thing. You're going to balance it just the way we did. But then we have to look at it and recognize that we don't have hydrogen ions. We have hydroxide ions instead. So wherever we have hydrogen ions, we're going to neutralize those by adding enough hydroxide ions to neutralize. So let's just do an example. So here we have iodide and permanganate ion. So I'm going to separate it into two half reactions. The I minus is going to go to I2. And the permanganate is going to manganese 2 oxide, no, manganese 4 oxide. Balance with respect to mass. Here I have 1 I and 2 I's. So I need 2 I's over there. I'm good. 1 manganese and 1 manganese, that's fine. 2 oxygens and 4 oxygens. I'm going to balance the oxygens by adding water. With 2 water molecules, I have a total of 4 oxygens over here and 4 oxygens over there. But that brought hydrogen in, and so I balance the hydrogen by adding hydrogen ions. So I need 4 hydrogen ions. Yep. Yeah.
Is that just to know how many hydroxides you'll need? Because you're not actually getting hydrogen.
Yeah, we're not actually getting hydrogen ions, but this is a much simpler way of getting to the right answer. Because if we try to balance with hydroxide, hydroxide has hydrogen and oxygen. And then it becomes icky, just really icky. So what I'm going to do is I'm going to do the whole thing as if it was acidic solution. And then at the very end, I'm going to fix it. I think that's easier. Sometimes I fixed it as I went along. I think it's easier to just fix it at the end.
So the way we know what to acidic or basic is the problem's going to tell us?
Yep, the problem will tell you. If it says acidic solution, it's easier. If it's basic solution, you do it the same way, 1 extra step at the end. So I have these balanced with respect to mass now. I need to put my electrons in. So here I have 2 negative charges, and over here 0. So I need to add 2 electrons to this side. On the bottom, these things are all neutral over here, so this is 0. And I have +4 and -1, a total of +3 over here. So I need 3 electrons. So I have 2 balanced half reactions. I need to put them together. When I put them together, I need the number of electrons transferred to be equal. Because if this one is giving up 2 electrons, this one can't gain 3. It has to be equal. So what's the least common multiple of 2 and 3? 6. So I'm trying to get to 6 electrons on both sides. And I find that I sometimes screw this up. And I'm figuring if I screw it up, you might screw it up too. So this one I need to multiply by 3. So I'm actually going to make a note to myself, multiply by 3. And the bottom one I need to multiply by 2. Otherwise, as I'm going through, I sometimes get carried away and do other things. So this will be a 6 and 3 and 6. I'm just multiplying all the coefficients by 3. Yes?
At first I put the 3 electrons on the other side. Does it matter which side? It's not because the negative 3 and 3.
Well,
What's that?
I mean, the 2 balanced half reactions, you're going to have 3 electrons on this side. And then I just need to fix it, whether I do fix the bottom one first or the top one first, doesn't matter. I just need to get them to be the same. Is that what you were asking?
So, like, without those 3 electrons on the left, it would be 4 positive and 1 negative, so that side would be positive 3.
Mm-hmm.
So I put the 3 electrons over here.
Okay. So instead of having instead of putting the 3 electrons here,
Wouldn't that make a negative?
you put them over here. And I can completely understand why you might do that, but does this give us the same charge on each side?
Oh, I was gonna make it go to 0.
Yeah, we're not trying to make it go to 0. It's an excellent point. We just need them to be the same. We don't care what they are overall, they just need to be the same. Yeah, I'm really glad you mentioned that. And if you're balancing and you find out that you have electrons on the same side for both your half reactions, you're doing something wrong. You should have one on the right and one on the left. Okay, so this bottom one I'm going to multiply by 2. So this is 6 and 8. 2. I'm multiplying by 2. I'm multiplying by 2. So I have 6 electrons and 6 electrons. That was my goal. Now when I add these together, I can cross out the electrons. I'm going to copy down what's left, which is most everything. Six I minus, 8 H plus, 2 MnO4, 3 I2, 2 MnO2, and 4 H2O. Not a bad idea to check that it's balanced. So here's our extra step. This is in basic solution. This is what we have with acid. We don't have an acidic solution. We don't have hydrogen ions floating around. So what I'm going to do is I'm going to look at my hydrogen ions wherever they are, however many there are, and I'm going to add an equal number of hydroxide ions. So I've got 8 hydrogen ions. I'm going to add 8 hydroxide ions to this side. And if I do it to one side, I don't want to mess up the balance. I'm going to add, no, it's not going to fit there, 8 hydroxide ions to this side. Now, what do I get when I put 8 hydrogen ions and 8 hydroxide ions together? I get 8 water molecules, right? So these guys, that's equal to 8 H2O. Do I have water anywhere else? I've got 4 waters over here. We don't need 4 here and 8 there. We could remove 4 of them. So I'm going to subtract 4 hydrogens from each side. 4 waters from each side. And now I can write my final equation. There's my balanced redox reaction in a basic solution. Yeah, right? Wow, exactly. So a lot of students hate this. I don't blame you. And there's another group of students that think this is like really kind of cool and like a fun puzzle. And I'll sometimes get students up at the board doing one together and they're arguing about it. They're just having a great time. So both kinds of people are great people. Just our brains work differently, and that's a good thing. One more. Right? Is that, yeah? Yeah, just the one more. One more. Let's do this one. So, make half reactions.
The last one on the right hand side.
Not sure if I can. No, I think I lost it. Yes, question.
It says plus 4 H2O.
Yes,
Below that you added 8
hydroxides.
Is
Mhm.
that because
That's because I added 8 hydroxides over here. And I chose to add 8 hydroxides because I had 8 H pluses.
right,
And I need to neutralize those.
and that became 8 H2O?
Right. 8 H2Os. And I had 8 H2Os and 4 H2Os. And I could subtract 4 from both sides.
But then 4 H2O plus 8 OH,
Yeah,
doesn't that add into something?
nope. This is water and hydroxide ions, and they're not going to react with each other. Yeah. Anybody else? Yes.
So you actually had 8 water molecules and 4 like, in the reaction, or
Right.
actually 4, but just to write it in those reduced.
Yeah, we want to write the final equation in the most simple form, because isn't it great when there's one correct answer, right? Instead of like 15,000 correct answers? Because I could write it is balanced with 8 H2Os and 4 H2Os, but I could also make it 1,700 H2Os on both sides. I mean, right? You could just get all kinds of ridiculous. And so what we want to do is we want to just get the very simplest form.
And then you can even say like H2Os is like a product.
Pardon me?
Like if you're looking at this as like a chemical reaction, now there's like no water molecules as like a product.
Right, because no water molecules are actually formed overall, right? 4 water molecules get broken down into other things, but water molecules don't actually get formed. So you can think of 4 of these water molecules as being like spectator ions. They're in there, hanging out, watching what's going on, but they're not actually participating. And there's actually like a gazillion others in the solution also watching. So why should those 4 be special, right?
They're imaginary water molecules.
Imaginary water molecules. They're like invisible because they're not actually doing anything.
Just like imaginary numbers in that.
Yeah. Okay, so let's do this one. Half reactions first. So, there's my arrow. So ClO minus on that side, and then I'm just going to pick whichever reactant is the most like that, right? This has chlorine in it, so I'm going to pick the chloride. Because I couldn't change chlorine into chromium, that just wouldn't work. So the other reactant here and Cr04 2 minus there. So we balance with respect to mass. So atoms, chlorine and chlorine, one of each. There's an oxygen here. And so we can add oxygens in by adding water molecules. So that gets me my oxygen that I need. So the oxygens are balanced, but it introduces hydrogens. We balance hydrogens with hydrogen ions. Even though this is a basic solution, we'll take care of it at the end. So now we've got H's, Cl's, and O's, same number on each side. So we do the same thing down here. 1 chromium and 1 chromium. Here I have 4 oxygens and 4 oxygens and 4 hydrogens here. So I need to put 4 hydrogens over here. I didn't need to add water in that time, that's okay. Now I'm going to balance charge by adding electrons. What do I need on the top? Two electrons over here. So I've got +2 and a -1. That's a total of +1 on this side, and I need a -1 to match that side. So if I have 2 electrons, 2 positives, and 2 negatives, those annihilate each other, and then I have -1 and -1. Down here, I have a -1 on this side. I have -2 and +4. And so that's something that we should maybe just write down. -2 and +4, and that is equal to +2, right? But over here, I have -1. So how do I make a +2 into a -1? I need 3 electrons. The math is not hard, but it's very easy to get confused. Now what do we need?
First thing, why did you add 3 electrons?
I added 2 electrons here because I need the total charge on the left side of the arrow to equal the total charge on the right side of the arrow.
And the right side is only -1.
Yes, and now the left side's -1 also. Because I've got writing with the eraser, -2, +2, -1. And over here I have -1. So -2, +2,